von Navimatix freuen uns auch, heute bei der Jena Digital Safari dabei zu sein. Mein Name ist Sandra Größler und bevor mein Kollege Andrea Entrizzi gleich mit seiner technischen Präsentation startet, möchte ich kurz ein paar allgemeine Worte über Navimatix sagen und Navimatix vorstellen. Die Navimatix GmbH ist seit fast 15 Jahren als Softwaredienstleister erfolgreich am Markt tätig und beschäftigt 35 Mitarbeiter. Wir decken den gesamten Softwarelebenszyklus ab, von der Konzeption über die Implementierung hin zu Betrieb und Wartung und auch der sich gegebenenfalls anschließende Erweiterung von individuellen Kundensoftwaresystemen. Zu den Bereichen, in denen wir tätig sind, zählt die Automobilbranche, der Bereich Transport und Logistik, die Optik und auch der medizinische Bereich. Zudem sind wir wissenschaftlich vernetzt und in Forschungsprojekten tätig. Das Forschungsprojekt ALEC möchten wir heute näher vorstellen. Dabei geht es um die Elektrifizierung aller Arbeitsgeräte und Fahrzeuge auf einem Flughafenvorfeld. Die Erprobung des Projektes erfolgt am Flughafen Erfurt-Weimar. Ja, und alles Weitere wird Ihnen nun mein Kollege Andrea Entrizzi erläutern, dem ich nun das Wort übergebe. So, I hand over to Andrea now.
Thanks. So, I hope you can hear me correctly. So today, I just want to give a brief overview of the ALEC project, as Sandra already said. Okay, so the concept of the project was to coordinate a fleet of electric vehicles at the Erfurt airport. And these vehicles should be treated as resources that have to be managed, and they're all jobs, tasks, and charging situations should be planned in advance so that they are following the best procedure, also to keep the power grid more or less evenly utilized during the day without too many spikes. This is not a single company project, it's a multi-company collaboration, and at Navimatix, we mostly took care of the application that connects the vehicle with the users and the Erfurt airport, as well as the Fraunhofer company, where the charging management part of this project is taken care of. Of course, since we are talking about vehicles, it's also useful to be tracking these vehicles. So the position of the vehicles will be part of the measurements that are being sent to the back end of the application and made available to the front end for the users and the administration people at the airport. So the vehicle fleet is currently consisting of only 3 vehicles, but each of them is equipped with a different machinery, which allows for most of the jobs that are required at a landing aircraft to be performed. So 2 vehicles have tanks and pumps that permit them to supply the aircraft with fresh water after landing, and also remove the disposal water that has been used for the previous flight. The third vehicle instead has a mechanical belt that is used to load and unload luggage from the aircraft. These vehicles, of course, can also perform different tasks, but for towing other aircrafts or the luggage carts, they would need to first remove the current equipment. So in order to communicate with these vehicles, we need some kind of onboard unit that allows us to exchange messages. And for this OBUs, we created a dedicated operating system image, and these units collect the vehicle information via the CAN interface and send them to our application. And they are also able to receive the charge plans created by Fraunhofer and translate them into something that the vehicle can understand how to show the user. Of course, they are always connected to our backend via a secure messaging connection. So here I want to just give a brief overview of the 2 main cycles or streams that are in the connector project. So from the vehicles, we receive measurements that are handled in our backend application and are then made available by the front end to drivers, but also to directly the airport administration. The other stream is information on which flights are going to land when in the next few days from the airport, which via mail server are reaching our backend, where we compute the necessary jobs that the vehicles have to perform, and we send the schedules of the vehicles we computed to Fraunhofer, who then answers to us with the charge plan, so when and where the best windows and charging spots are for the vehicle to use during the day in order to never run out of energy and to evenly consume energy over the power grid without stressing it too much. Of course, these charge plans are then sent to the vehicles. So these are the two front ends that we developed. On the left, it's the T web interface for the management, and T stands for Tour Energy Enhancement. And here we have high control over everything that is happening in the connector. We can check which jobs should be performed, which tours the vehicle are on, and for each vehicle we are able to check basic let's say measurements and telemetry, for example, the status of the battery, the vehicle status itself, and we have a map with the last known locations for the same day of the vehicle. On the driver side, instead, we have a simpler application, which is thought to be used on phones or iPads, and this shows less information, and a driver will only be able to see the information regarding its vehicle, their own vehicle, and not all the vehicles altogether. So in order to render more intuitive for the drivers, but also for administration to check where a vehicle is at any point, we mapped the airport and translated this way the coordinate position sent by the vehicle into a location that is humanly readable and more intuitive to understand for humans. So this is all well and good, but during development, we noticed that it's very important to be able to test all of these connections and all of these triggered events. So we decided to also create a small Java-based microservice that could substitute itself to the vehicles, at least in sending measurements to the backend. So we call this our vehicle simulator, although it's more like a virtual OBU. And this we can seamlessly insert in the measurement stream and allow our backend to receive data that we simulate, that we create. And since it's an application we have control over, we can both control which vehicles we want to simulate, for how long, how often we want to send data, which kind of data we want to send, and where do we want to send the vehicles running. So in order to have a proper simulation of what we expect to be happening in production, we created some tracks that allow us to, by composing them, perform simulations that represent the jobs that the vehicle would perform on a normal day at the airport. Of course, this is just a Google Map version of the map, but yeah, we have more tracks than what we use at the current time. So this is basically the result of running some simulations. Of course, they're very useful during testing because they allow us to simulate realistic measurements, and also, given we can control how often we are sending this information, it is very easy to test for different loads of traffic in our application and make sure that we are able to cover even higher loads than we expect normally. So it's resulting in a stabler app on the long run. Also, we can trigger multiple internal processes, like, for example, charge events, when are not always a measurement, they are evaluated by our backend. So by sending the correct measurements, we can check that when a vehicle plugs in, the correct charge event is sent to Fraunhofer so that they can evaluate better modifications to charge plans and so on. Of course, then we can also just populate the databases, and populating the databases, it's much easier to develop a front end. Here we are showing Grafana, which we use for tracking all the three vehicles of the fleet together. And as you can see here, we send the vehicles on a series of jobs, and the battery went down and then up when they start recharging. So it's consistent with what a vehicle kind of would do in real life. Now we prepared a small video to show the application working. So this is our service gateway web interface, and going to the flight data adapter, we can post a schedule of flights that we can then use to check that our application works and that we can send our simulated vehicles on real jobs. So from the T-Core web interface, we check that the jobs were correctly created. Each landing aircraft requires a set of different jobs. And then from the T-Core API, we can compute the assignment of jobs to the best vehicle for that job. Of course, electric vehicles have always precedence. Here, charge windows are also evaluated and sent to Fraunhofer. Then this results in a set of job executions and tours being created. And especially these latest tours are what is used by our simulator to then simulate the vehicles on realistic tours. From the front end, we can check that the jobs we created were correctly assigned so that the freshwater vehicle only got freshwater jobs. Now back to the service gateway web interface, we go to the vehicle simulator endpoints. Here we already created the 3 vehicles representing the electric vehicles. There they are, and they are connected to the entity in T-Core, so we can synchronize the tours pertaining to the vehicles on our simulator and then assign them each to the correct vehicle. Here we have created we have synchronized the correct tours, so there's like 6 jobs for each vehicle. And now we assign each vehicle to each tour and we start them. So now we send the vehicles on their tours, and they will not start until the first job starts. So here is from the other front end, the ALEC front end, one for drivers. You can see that when we refresh, as soon as the vehicles start running, the last contact changes, they are moving, and they reach the landing position very quickly because the distances in the airport are not very big. So again, from the administrative interface, we can check that the vehicles perform their task. They are already at the aircraft position, and they are now working on the aircraft. So they are still consuming energy because, of course, running pumps and mechanic belts requires energy. So this is, for example, the luggage belt job. Okay, then from the Grafana interface, we have a better picture of the 3 vehicles working together. So we can see that the energy battery is going down for all 3 of them at different speeds, in a sense, because different jobs, of course, require different energy to be performed. So if we wait for roughly 10 minutes, the faster jobs, so the water disposal and water supply jobs, have been completed. The vehicles drove back and are already recharged back to full and are now waiting at their own starting positions for the next job to be started. The luggage belt, of course, is longer, so we need to wait 40 more minutes for the second job to be actually finished, and the vehicle start driving back to its initial position, and it will soon charge to return to a reasonable amount of energy. So here again, we can see from the front end that the information is relayed also there, and the administrative front end shows perfectly that everything is going as expected. And in this case, you can also see that the other vehicle has now started charging. So I hope that this was enough to show that our application works, and that it's very nice to have some simulations that allow you to test it, and not only for the backend part, but also for the front-end side. So this was it for me, and thank you for your attention and for bearing with my English. So that's it for us, and thank you for the opportunity to speak at the Digital Safari.
Okay, thank you very much. Anna, do you have any questions?
No questions so far, but at this point, I'd like to encourage the community to post your questions in the chat or on social media or on YouTube, so we can hand it in to the talks. Also ich rufe die Community an dieser Stelle gerne nochmal auf, ihre Fragen einzureichen. Traut euch, seid nicht schüchtern, wir nehmen sie gern mit in die einzelnen Vorträge.